about the project title, Leaf Disease Detection based on Lightweight Deep Residual Network and Attention Mechanism. Introduction. Crop leaf diseases create significant challenges in agriculture. These diseases directly contribute to decreased crop yields, which affects overall production. Moreover, to combat these diseases, farmers often resort to increased pesticide usage, which not only raises production costs but also has environmental implications. Traditional deep learning algorithms encounter difficulties in accurately identifying disease features within leaf images. The variation in lesion sizes and their scattered locations across the leaf surface poses a significant challenge. As a result, these algorithms struggle to precisely extract and interpret disease-related features from the images, hindering accurate disease identification. To address these challenges, the project introduces SCVRNet, a specialized lightweight deep residual network. SCVRNet is a fusion of two key components: VRNet, Variant Residual Network, a deep variant residual network tailored for effective feature extraction. SC module with attention mechanism. This module, known as squeeze and excitation, integrates an attention mechanism that focuses on significant features while squeezing irrelevant information. The primary objective of SCVRNet is to revolutionize the extraction of critical information from leaf images. Specifically, it targets the precise extraction of the region of interest where the disease is located and lesion details. By doing so, SCVRNet aims to significantly enhance the accuracy and efficiency of identifying leaf diseases. Objective. The primary goal of the project is to significantly improve the accuracy of identifying crop diseases from leaf images. This improvement is facilitated by the utilization of a specialized lightweight deep residual network known as SCVRNet, coupled with an attention mechanism. This combination is aimed at elevating the precision and reliability of disease identification compared to conventional methods. While aiming for heightened accuracy, the project also prioritizes computational efficiency. The goal is to ensure that the developed system remains practical and usable in real time or for large-scale agricultural applications. This optimization enables the potential deployment of the system in scenarios where timely disease detection across extensive agricultural areas is crucial. A critical aspect of the project involves addressing the limitations faced by traditional deep learning methods. By concentrating on a wide array of disease-related features present on leaves, the project seeks to overcome these limitations. The system aims to effectively extract and interpret these varied features, potentially enabling more comprehensive disease identification compared to conventional DL approaches. The ultimate objective of the project is to develop a reliable tool that benefits farmers and agricultural experts. This tool's capability to detect disease early in their development stages facilitates timely interventions. Early detection minimizes crop losses, thus enhancing overall agricultural yield and ensuring sustainable production practices. Integrating an attention mechanism into deep learning methodologies represents a novel and innovative approach. This mechanism allows for selective focus on specific features within leaf images, potentially revolutionizing disease detection methods in agriculture. This selective attention facilitates a more nuanced and precise interpretation of disease-related features, contributing to heightened accuracy in disease identification. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules of flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary libraries and packages within chosen programming environment. Commonly used libraries like NumPy, Pandas, TensorFlow, or PyTorch are imported here. These libraries provide essential functionalities for data manipulation, model building, and image processing. Exploring the dataset, plant village, and self-data. These modules involve exploring and understanding the datasets. Plant village typically comprises labeled images of various plant diseases, while self-data includes a combination of curated datasets of manually collected data. Understanding the dataset involves checking its structure, inspecting sample images, and comprehending the distribution of classes or categories within the dataset. Image processing. Using image data generator. This is a feature-rich utility in deep learning frameworks like Keras that generates batches of augmented image data. It's commonly used for training deep learning models with image data. It facilitates real-time data augmentation, enhancing model generalization and robustness. Rescaling the image, shear transformation, zooming the image, horizontal flip, and reshaping the image. These are specific image processing techniques applied using tools like OpenCV or built-in functions within deep learning frameworks. Rescaling ensures uniformity in image sizes, shear transformation introduces distortions, zooming modifies image magnification, horizontal flip adds variations, and reshaping aligns images to a specified format or size suitable for model input. Feature extraction using Torch Vision. Torch Vision is a package in PyTorch which offers various functionalities for computer vision tasks. Feature extraction involves using pre-trained models such as ResNet, BGG, etc. available in Torch Vision. By employing these models, one can extract high-level features from images, potentially leveraging these features for further analysis or feeding them into custom models for disease identification. Transforms to random horizontal flip. This transformation randomly flips images horizontally during training. It helps augment the dataset and prevents model overfitting by exposing the model to different orientations of the same image. Random rotation. Similar to other augmentation techniques, random rotation introduces variations by rotating images at random angles during training. This augmentation aids in improving the model's robustness by exposing it to different orientations of the same image, helping prevent overfitting. Conversion to tensor. Converting images into tensors, which are multi-dimensional arrays, is essential for feeding data into deep learning models. Tensors are the fundamental data structure used by deep learning frameworks like PyTorch or TensorFlow, enabling efficient computation and manipulation of data. Resizing the image. Resizing involves adjusting the dimensions of images to a specified size suitable for model input. This step ensures uniformity in image dimensions, aligning all images to a consistent size before feeding them into the model. Building the model. This step involves constructing the architecture of the lightweight deep residual network (SCVRNet) along with the attention mechanism. The model architecture defines the layers, connections, and operations that the neural network will perform to extract features and make predictions from the input data. Training the model. Once the model is built, it needs to be trained using the prepared dataset. During training, the model learns from the dataset by adjusting its internal parameters, weights, and biases to minimize prediction errors. This iterative process involves feeding the training data through the model, computing loss, and optimizing the model's performance using optimization algorithm, example gradient descent. Flask framework with SQLite for sign-up and sign-in. Flask is a web framework used for building web applications in Python. In this context, Flask is employed to create a user interface for the leaf disease detection system. SQLite, a lightweight relational database, is integrated into Flask to manage user authentication. Users can sign up, creating accounts, and sign in securely to access the system's functionalities. User upload an image for analysis. Users interact with the system by uploading leaf images they want to analyze for diseases. This step typically involves an interface where users can select or drag and drop images from their devices to initiate the analysis process. The given input is pre-processed. Once the user uploads an image, the system pre-processes the input image. This involves applying the same image pre-processing steps discussed earlier, such as resizing, converting to tensors, and any necessary transformations to prepare the image for model prediction. The trained model is used for predicting the result. The pre-processed image is fed into the trained SC-VRNet model and the attention mechanism. The model then predicts the likelihood of disease presence based on the image features learned during training. Final outcome is displayed. Finally, the system displays the outcome of the analysis to the user. This includes information about the identified disease, the confidence level of the prediction, and any recommended actions or interventions. As an extension, we applied deep learning methods to produce a more robust and accurate final prediction. Algorithms used. The following algorithms are used in this project. GoogleNet introduces inception modules comprising parallel convolutions for varying sizes, promoting efficient information capture at different scales within the same layer, optimizing computational resources while preserving accuracy. ResNet proposes residual connections that pass the input through layers via skip connections, mitigating degradation issues in deep networks, enabling the training of extremely deep networks with improved convergence and representation learning. AlexNet breaks ground as one of the earliest deep CNN convolutional neural network architectures, featuring multiple convolutional and fully connected layers, employing techniques like ReLU, activation, and dropout, pioneering deep learning for image classification tasks. BGG16 comprises 16 layers with a stack of 3x3 convolutional layers, emphasizing depth in convolutional neural networks, creating a straightforward architecture with homogeneous structures that excel in feature extraction. Exception 45 and Exception 139. Extreme inception focuses on depth-wise separable convolutions, refining the inception concept by separating spatial and channel-wise operations, potentially reducing computational complexity and enhancing information extraction. ResNet 18 and ResNet 134. Variant ResNet architectures with 18 and 34 layers respectively, offering different depths while maintaining the residual connections benefits, providing options for varying model complexities. VRNet 18 and VRNet 34. Variant residual networks with 18 and 34 layers, potentially fine-tuned or adjusted from the standard ResNet architectures to address specific task requirements or efficiency consideration. SC VRNet 18 torch-based pre-trained model and SC VRNet 34 torch-based pre-trained model. Extends VRNet architecture by integrating squeeze and excitation modules and attention mechanism. Pre-trained using PyTorch, aiming to enhance feature extraction and channel-wise attention within the network for improved disease-related feature detection in leaf images. Comparison graph of plant village dataset. In this project, we have utilized plant village dataset. It is a well-known and widely used dataset in the field of agriculture and plant pathology. It comprises a diverse collection of labeled images depicting various plant diseases, pests, and nutritional deficiencies across multiple plant species. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy measures the proportion of correctly predicted instances among the total instances in a dataset. It provides an overall assessment of model performance, indicating the ratio of correct predictions to the total predictions made. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision calculates the ratio of correctly predicted positive observations to the total predictive positives, focusing on the accuracy of positive predictions. It measures the model's ability to avoid false positives, indicating how precise the model is when it predicts a positive outcome. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall computes the ratio of correctly predicted positive observations to the actual positives in the dataset, focusing on the model's ability to capture all positive instances. It assesses the model's capability to avoid false negatives, indicating how well the model captures all actual positive instances. This is the F1 comparison graph. On the x-axis we have the F1 score, and on the y-axis we have the algorithm name. F1 score combines precision and recall into a single metric, calculated as the harmonic mean of precision and recall. It balances both metrics. It provides a balanced assessment of a model's performance, particularly in scenarios where there's an uneven class distribution, aiming to find a balance between precision and recall. Comparison graph of self-data dataset. In this project, we have utilized self-data dataset. Self-data encompasses a combination of datasets related to plant disease, potentially merging information from various sources such as plant village, other research dataset, or data collected through field surveys. It includes images, annotations, metadata, or additional information relevant to leaf disease in crops. This is the accuracy comparison graph. On the x-axis we have the accuracy score, and on the y-axis we have the algorithm name. This is a precision comparison graph. This is the recall comparison graph, and this is the F1 comparison graph. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook files. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the File Explorer. Here, I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally. At the default address, which is the localhost this, and port, which is this. Now copy this local link provided by the Flask framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome. And hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up. Here we need to enter all these details to register. But I have already registered, so click on sign in. Here we need to enter the username and the password which we have created, and then click on login. We have logged in successfully. So here we need to upload the leaf image, and after uploading the image, we will predict the plant leaf disease. So click on choose file. I have selected this image and then click on open. So this is the leaf image which we have uploaded. Now click on upload button. So here we can see leaf is infected by peach bacterial spot disease. Let us upload some more images. Click on choose file. Click on upload. So here we can see leaf is infected by peach bacterial spot disease. Let us upload some more images. Click on upload. So here we can see leaf is infected by apple scab disease. Click on choose file. Click on upload. Leaf is infected by cherry including sour disease. Click on upload. So here we can see leaf is infected by corn maze northern leaf blight disease. So in this way, by uploading the leaf images, we can predict the leaf disease. Click on sign out. The conclusion of the project is the SC VRNet model combining VRNet variant residual network and SC squeeze and excitation module achieves remarkable accuracy in detecting leaf disease, particularly when deployed on mobile devices. Its architecture, blending these components, is optimized to effectively extract critical features from leaf images, enabling precise disease identification even with limited computational resources on mobile platforms. Through rigorous experimentation across datasets like plant village and self-data, the SCVRNet model showcases its superiority over existing methods in leaf disease detection. Comparative analysis against other state-of-the-art methods affirm SCVRNet's efficacy, establishing it a more accurate and reliable solution for identifying leaf disease across different datasets. A key focus of the SCVRNet model's development is its deliberate design for mobile compatibility. Its lightweight architecture ensures efficient performance on mobile devices without compromising accuracy. This emphasis on mobile deployment is crucial for practical applications in agriculture, enabling real-time disease identification and intervention using portable devices. The project's use of cross-validation techniques stand as a testament to the reliability and robustness of the leaf disease detection accuracy assessment. Cross-validation involves systematically partitioning the dataset into subsets, ensuring that the model's performance is consistently evaluated across different data splits. This methodology enhances the reliability of the accuracy assessment, ensuring that the reported results are more generalized and less affected by chance.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.